All right, welcome everybody. Let's get started with today's installment of our lecture on image processing, retrieval, and so on. Here is the overview. Again, we will begin by looking or reminding ourselves about what we have been discussing last time. And well, we have been talking about coordinate systems in the end. And today it's time to put our newfound knowledge to work. That is, today we will begin discussing transformations. In particular, we will look at affine transformations and in how far they are related to what we would call matrix operations. And we'll summarize and we are done for today. Let's see what all of this includes. So this is another brief motivation of our long-term goal in this lecture. In the end, like once we are done, once the semester is over, we want to understand how we can turn something like this into something like that. How we can manipulate an image like this one, such that afterwards it looks like that, for instance. And I have said it in the very first lecture, the overarching topic of this whole lecture series is transformations. And so now it's time to look into what that may mean. And if you remember, in the last lecture, we spent quite a lot of time on discussing this abstract concept of a vector space. Right? We said that a vector space is something, a triple, that consists of a set V, which we shall call the set of vectors. And at the same time, there is supposed to be an operation, let's call it plus, and another operation, let's call it times, such that if we, I don't know, apply this operation plus to two elements in V, we obtain another element in V. And for instance, if we multiply a scalar to one of the elements in V, we obtain another element in V. And then there were certain other basic properties of a vector space we require. A couple of actions with respect to addition and with respect to this operation of multiplication. And whenever we are considering some set V for which there is something like an addition and something like a multiplication, and these operations of addition and multiplication meet all these actions we have been discussing, then we are discussing or considering a vector space, right? And the important thing, or the thing I did want to hit home last time, was that vectors are more than we typically think they are. Right? When we first learn about vectors, they occur in form of tuples of numbers, well, vectors, right? And we then learn how to, I don't know, add vectors and transform vectors, and whatever we do with these, let's call them geometric vectors. But the important thing I stressed was that this structure and the corresponding actions is met by more objects than just these tuples of numbers, which we learn when we first encounter vectors. In particular, we saw that we may think of functions as vectors as well, and this will become important later on. And we saw, in addition to our discussion of elementary vector spaces, that if we are able to endow these vector spaces with another operation, which we shall call the inner product, an operation that acts on two elements in the set V and produces a scalar, whenever we are able to define such a product, then we are actually talking about an inner product space. Now, once we have defined an inner product, and we saw examples as to how they may look like, and that indeed there are more inner products than the one we learn about when we first learn about geometric vectors. There are more inner products, but once we have defined that notion of an inner product for a vector space, then we can actually also induce a norm. That is, we can talk about the size of vectors, and that is, if we are able to define a norm, typically this function here is derived from the inner product. So we reminded ourselves about the notion of vector spaces, inner product spaces, norm spaces, and the crucial thing is we saw that these concepts are way more general than we may have thought when we first learned about them. Another very elementary idea we discussed in the last lecture was the notion of a distance. And in particular, we discussed that if we are considering elements, say, x and y in some vector space, and I am not specifying what kind of vector space. This is a very abstract discussion here. Some vector space, and we are able to define a function, let's call it d of x and y, which, if we compute it for x and y, produces a scalar in some field k. That can be the real numbers, that can be complex numbers, does not really matter. But if we are talking about a set of vectors, and we look at two of them, and we have a function d that has the following properties: that it is always greater or equal than 0, and in particular that if it evaluates to 0, that can only happen if these two objects are the same. First crucial property we require of a distance. The second one is that it is symmetric. That is to say, it doesn't make a difference if we compute the distance from x to y or the distance from y to x. Should be the same result. In that sense, this function has to be symmetric. And then finally, it has to obey this so-called triangle inequality, which is to say, if we consider three objects in this vector space, x, y, and z, and then we look at the distance from x to y, or the distance of x and z, then this expression should always be less or equal than the distance of x and y and z. If we are talking about a function applied to vectors, whatever kind of vector space, we don't really care, that meets these requirements, we are talking about a distance. And we then continued now, having sort of recalled all these elementary ideas, we then had a look at another very elementary idea, and that is the notion of a point. Right? And a point is a geometric object. It is something that is infinitesimally small, like dimensionless, but it has a location. It is somewhere. It does not have an extension or whatever, but it is located somewhere. It's a point. And we discussed the idea of coordinate systems, and that we are able to express points in terms of coordinates, and that there is somewhat of a duality between points and these geometric vectors if we think of vectors as oriented line segments. So like oriented line segment. Line segment is something that has a start and an end, and an orientation is to say, well, it points somewhere. So if we consider geometric vectors as oriented line segments, then we may indeed identify points and vectors, and I will do this from now on, so you shouldn't be shocked if I do that. And finally, this was something we already discussed when we looked into norm spaces, the idea of a unit vector. Whenever we are talking about a vector, again, independent of what vector space we are actually considering, but if this vector space is a norm space and the vector we are looking at has a norm of 1, then this vector is called a unit vector. And now having sort of familiarized ourselves with points and vectors and unit vectors, and the fact that we can think of vectors as oriented line segment, geometric vectors as oriented line segments, we could then sort of make more precise what we actually refer to when we're talking about a coordinate system. Right? And we said that a coordinate system has an origin that is a certain point. In this case, the point is here. That is the point we call the origin of this coordinate system. This coordinate system would have this origin, and so on and so forth. So a coordinate system consists of an origin and a set of axes. In our case, this is a two-dimensional space or a plane. So here, all we need to specify a point in this plane is two coordinates, which is to say we need two axes. And here we see examples of such axes, and we already see that these axes are not always perpendicular. Second requirement for a coordinate system is to have axes, and the third one is to have the notion of a unit length. Like what is it to say this is the point 1, 1 in this coordinate system. So we have to, for every coordinate system, sort of fix what we mean by 1. And particular note that apparently the notion of 1 in this system is a different notion than in this system. That sounds crazy and abstract, but 1 can mean different things. Now, once we have that, and we discussed these oblique systems ever so briefly, we can work with them, but it's a bit of cumbersome exercise and not really necessary for our purposes. If we're doing special and general relativity theory, then we would have to consider these oblique systems. We don't have to do that. So we can focus on the idea of Cartesian coordinate systems, and Cartesian coordinate systems are special coordinate systems in that their coordinate axes are perpendicular. The angle between these two lines or between these two vectors is 90 degrees, or pi over 2, and they are positively oriented. That is to say, once we agree that there is sort of a first axis, let's call it x in this case, and we want to somehow say rotate this first axis onto the second axis, then we have to return it like this. That is, our thumb of the right hand becomes the axis of rotation. That is what it's meant when we say positively oriented. So if it was this, then it would be anti-positively oriented. We have this. In the case of U and V, it's also like this, actually for all of them, Q and R, they are all positively oriented. Third thing about a Cartesian system is that the unit length is indeed the real number 1. Okay. Something that will be important today is that we have to wrap our head around the idea that there is a certain point, and we can talk about this point from different points of view. For instance, if we assume the point of view of this coordinate system, we have fixed that. However we did that, then this point would have an x-coordinate somewhere about here and a y-coordinate somewhere about here. But if we want to talk about this point in this system, we could say it has a q-coordinate somewhere here and an r-coordinate somewhere here. That is, when we are talking about this point in terms of two numbers, let's call them coordinates, these coordinates depend on the coordinate system we use in our discussion. But the point is always the same. Right? It is just a different perspective we have on the point. We don't move the point around, in a sense, we just move our reference frame. And here's some more on this duality between points and vectors. These again are very general concepts that apply to any kind of vector space, but right now we will focus on these Euclidean spaces, on these spaces we can express in terms of Cartesian, or we can discuss in terms of Cartesian coordinate systems. So if we're talking about, let's say in this case, an n-dimensional space, this is a two-dimensional one. In general, we can talk about arbitrary dimensions. And we would have a set of vectors, n of them, let's call them E1 all the way up to En, and they are linear independent, where again the notion of linear independence means that if we look at linear combinations like that, that is, we have scalars which we multiply to these vectors, and we have additions where we add another vector to this one, and so on and so forth. These vectors were linear independent if we want the result of this operation to be 0, and if we can only achieve that if all of these numbers are 0, then they are called linear independent. If they are linear independent, we say that these vectors span the space, that is, every point in this space we are discussing can be expressed as a linear combination over these basis vectors. And these coefficients here we use in this linear combination are then called the coordinates of this vector. And there you have it. This is just a very elaborate way of saying that we may think of a point which has coordinates with respect to some coordinate system. We may think of such a point as a vector which has coefficients with respect to a basis system. Right? This is, yeah, it sounds more involved or complicated than it is, but yeah, this is how it is. Right? The very deep insight behind these two slides is actually that we can sort of bring together geometry and algebra. That was actually first discovered, I don't know, recognized by a guy called Descartes, a French name, which is why this is called Cartesian systems, who realized that up until, I don't know, 200, 250 years ago, when people did geometry, they did that with lines and circles and triangles and whatever, but not in terms of plus and times. Geometry and algebra were two different things. But once humankind wrapped their heads around the fact that we can talk about geometric objects in terms of, say, coordinates in Cartesian systems or in coordinate systems, that build a bridge to what we call linear algebra, where we are talking about vectors and linear combinations of vectors. And there you have it. Geometry and algebra can be treated as the same thing, which is great because whenever we can do addition and multiplication and whatever, we can do really a lot of mathematics. With the computers we have, we of course could also do mathematics just using rulers and circles and whatever, but that would be more difficult for our computers. Now, and today we will begin to look at what all of this buys us. We have now laid the foundation. We can talk about points in terms of vectors. We can think of points as coordinates in some coordinate system, which is great because if we are talking about functions, we always like to think about functions as being defined over some domain. For the case of images, the domain is the two-dimensional plane. Now we know that we can refer to points in the plane in terms of coordinates and vectors, and now we can think of transforming coordinates and vectors, and then maybe that might lead us to being able to transform the appearance of an image. Now, the first kind of transform we will be discussing are the so-called affine transformations. We can think of them as a way of translating a coordinate system, let's call it O x hat y hat, into another coordinate system. Let's call it O prime, X hat prime, Y hat prime. And basically, again, this is just a very fancy way of saying, say we have this point and it is currently expressed in this coordinate system, then we may do some mathematics in order to express this point in this coordinate system. And this is what I mean by translating one system into the other. Like what kind of operation would it require to express this point, which we have measured in terms of its x coordinate and its y coordinate? What do we need to do to express it in terms of an s coordinate and a t coordinate? And again, these coordinate systems do not have to be Cartesian systems. They may be any kind of coordinate system, that is, they may have different ideas of unit lengths, and they might be oblique. And yeah, well, I'll skip that. We'll come back to that later, much later. The affine transformations are special in that they are rather simple, and they have certain properties which we'll look into throughout this lecture today, which sort of make them stand out and make them sort of easy enough so that we can actually begin our discussion of all of this with the affine transformations. Examples of affine transformations are identity mappings, that is doing nothing. This is always the most popular transformation in mathematics. We have something, we want to do something, we don't do anything with it, and it's a transformation. Doing nothing is called an identity transformation. Affine transformations include rotations, scaling, shear, reflection, and translations. And any combination of these elementary transformations is another affine transformation. And this is a picture says 1,000 words. Here are examples. This is something. Let's call it, I don't know, probably let's call it an image. Why not? And we have a coordinate system. And there are apparently 4 points. I have somehow singled out, sort of just by drawing this rectangle. Our brains should be able to see the 4 corners of this rectangle. And now let's see how these 4 points look like if we apply different kind of affine transformations. First of all, simplest thing we can do is doing nothing. Nothing will happen. Everything will look the same. And this is what we obtain if we apply a rotation. I have rotated this thing by a rather small angle. Now, and I have to discuss this particular case in order to make sure that well, yeah, everything is okay with what we're discussing today. It looks like, so if we look at this, it looks as if this thing has been rotated, right? But I would encourage you to tilt your head like so and look at this one, right? I said an affine transformation translates one coordinate system into another one. There are 2 ways of thinking about these kind of transformations. We can think of them as we are given an object and a coordinate system, and then we apply an affine transformation to the object and look at the object in the system we started with. Then it will look like this. Right? Or we may sort of think of these affine transformations as rotating, in this case, rotating these coordinates, these axes. Right? This is indeed the same thing. And it would not make a lot of sense if I were to just rotate this, because then this, you know, would just be rotated and we could not see what I really mean by rotating something. So all these sketches here look as if I had done something to the object. But we may as well think of these sketches as this here being another coordinate system. In particular, the one if you tilt your head like so. Right? Now, we can rotate things, we can scale things along one of the axes, we can scale things along the other axis, we can scale things along both axes. All of these are examples of what we call affine transformations. We may shear things, so the object would look like this if we shear it along the x-axis. This is a shearing operation along the y-axis. We can do this with respect to both axes. We may reflect objects along one of the axes, reflect them along both axes, and we may actually move objects around. And if we do any arbitrary combination of all of these things, we may indeed actually also obtain something like that. And yeah, this is something that looks silly. Can we do that with images as well? Yes, we can, and we will learn how to do that later on. This is just sort of to motivate that once we are done with all of this, we know how to do this. Here is the original image. Here I have scaled it, and apparently I have sort of shrunken it, and this is indicated by the fact that now the original size was from here to here and here to here, and I sort of sketched the original size here as well. But if I minimize this and plot it in the corresponding coordinate system, I wouldn't know what to plot here, so I set it to black. That's an artifact of how we would visualize this. Now I have scaled the image, no problem there. I may shear it. Right? So first we scaled it, then I apply the shear operation, and then I translated it a bit, and then I rotated it, some rotation, and then I flipped it. There you go. Can all be done. And we will learn how to do this with actual images later on. For now, we have to understand what is under the hood here. What are the underlying principles? And to do this, we single out a particular affine transformation, namely the idea of rotating coordinate systems. And we will focus our discussion on this very elementary case of two-dimensional coordinate systems, that is, coordinate systems that allow us to talk about objects in a plane, that is, systems that have one axis and another one. Of course, I will assume that these systems are Cartesian, so the axes are perpendicular. Now, in this sketch, we see two systems, and I call them, the first one is S subscript UV, consisting of this origin and then the two axes or unit vectors that sort of span this system, u hat and v hat. And the second one is S subscript xy. The origin is the same, no? And the axes are different. Right? Here we are talking about the x hat and the y hat axis. And just from looking at this figure, it appears that the difference between these two systems is that the orange one is rotated away from the blue one by an angle of phi. Phi is yet another Greek letter. For those of you who have never seen it, the Latin corresponding letter would be F. But this is phi, quite often used in these contexts. So we're talking about a problem where we are given a point, P, and two coordinate systems, u hat, v hat, x hat, y hat, where x hat, y hat is rotated away from u hat, v hat by an angle. And with respect to the coordinates of the point P, that means that the coordinates with respect to u and v are pu here and pv here, and with respect to x and y, they are px and py. And px is a different number than pu, and py is a different number than pv. But the point is the same. This is important. The point is the same, but there are in this sketch already two ways of how we can talk about the point. We can talk about the point using these two numbers, pu, pv, or these two numbers, px, py. And the question we will look into right now is it possible for us to compute, say, px, py if we are given pu, pv? Is there a way how we can express the point in px, py if all we know is pu, pv? Can we do that? And how would we do that? And this is so fundamental that I will do that step by step. Yeah. Take a minute and let this picture burn into your heads, or maybe make a sketch. Switch on the lights. All right? So, first thing to note is that I will treat this point as a vector. Right? And on the whiteboard, I write vectors with this underline thing here. On the slides, it's always like these bold letters, but I cannot really draw bold letters on the whiteboard. So this is now a vector, but I said I will identify vectors at point. That is something we'll assume right now. And given that picture that just disappeared, we have, think of it, we have that this point P can be expressed as, I should have them, the vector x hat times the px coordinate plus the vector y hat times the py coordinate. And the crucial thing is that this vector can also be expressed as the vector u hat times the pu coordinate plus the vector v hat times the pv coordinate. And I could stop here and hand it over to you because this one here is really what we need to internalize. That from the point of view of this point or vector, it does not matter if we talk about this point in terms of the x, y coordinates or in terms of the uv coordinates. I can really put an equal sign in between here. This is the same. Both these expressions give us this. Okay? And because this is so, we can now begin to play with algebra. In particular, we can compute an inner product with both sides of this equation. And well, yeah, inner products are also often called dot products. So what I say here is dotting with the vector x hat yields, well, dotting with x hat is to say that I will compute the inner product of both sides of this equation. Like, let's write it so, with the vector x hat. So far I have written inner products using this pointy brackets, and I will do this in this line here. So if we compute the inner product of this first term with x hat, we have x hat inner product with x hat times px. Right? This is a vector, this is a scalar. If we compute the inner product of this scaled vector with another vector, it's basically the inner product of the vector with this vector times the scalar. Okay? And here we get y hat times x hat times py, and on the right hand side we get u hat times x hat times pu plus v hat times x hat times pv. All right. And the reason why I am writing inner products like that is because we will later on consider inner products between functions, and then it does not make sense to use this thing, so get used to it. If you haven't seen it, this is basically, this is the same. I'll make a box here once again. If we are talking about something like this, this is the same as, you may know it as this, inner product of x and y, or is also the same as x transpose, y transpose. It doesn't matter. It is just notation, right? But I am using this notation because it will come in handy later on. All right. But what do we got here? First of all, we recall that the inner product between two vectors that are perpendicular or orthogonal is 0. But y hat and x hat are orthogonal. So this goes away. This is 0. Right? And here we have the inner product of x with itself, which is basically the norm squared of x. But x is a unit vector. Its norm is 1. 1 squared is 1. So this whole equation boils down to, this here is 0, this is 1. Let me 1 that. So we have, px is inner product of u hat and x hat times pu plus inner product of v hat and x hat times pv. Okay, we can repeat this exercise instead of using x hat, using y hat. Right? So if we were to dot this equation with y hat, we would similarly get, doppelpunkt, we get in the end that py is the same as u hat times y hat times pu plus v hat times y hat times pv. I didn't do that, right? We see that basically if we were to dot this with y hat, we would get a 1 here and a 0 here, but so it's the same. Can't do that. This is the first interesting observation, because if we do that, we end up with two equations. And in particular, these are linear equations. There is just a multiplication here and an addition and another multiplication here. So there's like no square roots, no squares, no exponential, no nothing. It's just something times something plus something times something. This is what we call linear equations. And we have two of them. And we know that once we're talking about systems, in our case very small system, just two, systems of linear equations, we may express them in terms of matrix vector equations. Let me do that. Keep that as a reference for a second. So in matrix vector notation, we can express this as a vector px, py, this is on the left-hand side of the equal sign, is given as the product of a certain matrix, and this matrix is u hat x hat in a product, v hat x hat in a product, and here we have u hat y hat in a product and v hat y hat in a product times a vector pu pv. It's just another way of writing down this system of two equations. And now that we are here, we note the following. We note that, and this is something I hope you know, the inner product between two vectors, and let's be specific here, say u hat and x hat, is or can be expressed as the norm of u hat times the norm of x hat times the cosine of the angle between them, right? But this angle between them is phi, given the picture we just saw. And we also remember, once again, that these two vectors are unit vectors. So all of this inner product here, actually boils down to cosine of phi. Okay? What about the inner product between v hat and x? V hat and x hat. First part is obvious, it's v hat, norm of v hat, times the norm of x hat times some cosine, must be an angle between the two of them. And if you look at this figure you probably took a sketch of, or we had on the projection here, the angle between these two vectors is actually phi plus 90 degrees, which I will write fancily as pi over 2. Pi over 2 is the same as 90 degrees. Let me draw this again. It's not visible. So, angle between v hat and x hat is phi plus pi over 2. And again, oh wait, minus. Sorry, I skipped a line here, so we have actually pi over 2 minus phi. Yeah, so thank you. So this will happen quite frequently, right? So it's your job to say, hey, wait a minute, I'm just, I'm here for the bigger picture, you're for the details. So this is indeed pi over 2 minus phi. Sorry about that. Let me immediately make it up for you. If we look at the inner product between u hat and y hat, now we have u hat norm times y hat norm times, and here we have cosine phi plus pi over 2. I guess this is the right one, yeah. Okay, and finally, make it here, inner product between v hat and y hat is the norm of v hat times the norm of y hat, and here the angle is just, again, phi, right? So, basically all of this, since all these are unit vectors, their norms is always 1, I can simplify this to cosine pi over 2 minus phi. This one is cosine pi over 2 plus phi, and here we have cosine phi again. All right? No big deal so far. It's basically to say that in this matrix here, which so far I have written where the elements are expressed in terms of inner products, I can now plug these things in here. Okay? No problem. But some of them, yeah? Question? No. But I will not do this right away because what is cosine pi over 2 minus phi? It's not like that. To simplify that further. Anybody already any idea? Exactly. Exactly. Very good. Very good. Why is that? Because we recall the addition, or one of the addition theorems of cosine and sine. In particular, if we have cosine of some alpha plus minus some beta, again Greek letters here, this is the same as cosine alpha times cosine beta, and then minus plus sine alpha sine beta. And we also recall that cosine, what do we have? Pi over 2, say. Pi over 2 is minus 1 over 2. And what else would we need to make sense of these things? No, what?
Pi over 2.
Pardon?
0.
One at a time. 0. I would, whatever. Like again, might have this. It's too dangerous here to discuss these details for me. I'll just plug in. So we make sense the use of this and obtain in the end. Check it out. I'm sure actually I do. But you know, these are things I don't really worry about. I recall that cosine pi over 2 is minus 1 over 2, but if it's not, then I don't care. I know that there is some simple expression for that. You figure out the details, but you know what I'm after here. You know what I'm after here. So we use this to further simplify what we had there. And in the end, get that this vector px, py can be expressed as a matrix cosine phi, sine phi, minus sine phi, cosine phi, times pu, pv. Have you seen this before? Yeah. Have you seen where it comes from before? But now you know where it comes from, right? It's like, this is really, now this is what I'm trying to hit home. If you read about these things in some books, they say, yeah, the rotation matrix, blah, 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 is given like this. But why? They never tell you. And now you have seen it. It's like really straightforward algebra. And this is the great thing. Again, that if we are talking about geometric objects such as points, in terms of algebraic objects such as vectors, we can do geometry using algebra, in particular linear algebra. Here we are. This is what we would have to do if we're given the point P in its UV coordinates. Say we know the angle phi by which the other system is rotated away, then we can apply this operation to the vector to get the vector in xy coordinates. Okay? And I don't really want to continue writing these eight symbols all the time, so I'll simplify that. Instead of px, py in terms of a vector with two coordinates, I may just write vector pxy to indicate that I'm talking about the vector in the px coordinates. It's vector p, but now expressed in terms of px coordinate, times a matrix. I'll call it R phi. Note that I'm indicating matrices with these two underbars. It's for you to be able to see that this is a vector, this is a matrix. R phi times P UV, right? But this is still too much symbols for me, so I will further simplify it to vector x equals matrix R times vector U. All right? And it's crazy because when I'm writing x here, I'm actually talking about p. But this is to say this is vector p in terms of its xy coordinates, and this is vector p in terms of its pu coordinates, uv coordinates. All right. But I'll, you know, from now on, that's what I use. Okay, what do you know about rotation matrices? Are they special? I mean, just some of you mumbled and jumbled that you have seen this before. What else have you seen before when you're talking about this? You don't have to answer. Let me point out certain properties of this matrix R. The reason why I am singling out this affine transformation, this rotation, we've been talking about shearing and scaling and all this, they are all boring. This is the one that is of importance in all of science. And we'll come back to other manifestations of that in a couple of weeks. And so basically, if what we did just now, if you can accept that, and if you can wrap your heads around what we did here, you don't have to worry. Right? Basically, everything else that is to come from now for the next couple of weeks is making this more complicated. And that's all there is. Why is this a special matrix? Well, I already said it. It is a rotation matrix. R is a rotation matrix. Now, why is that special? Like, what is it to say that a matrix is a rotation matrix? That is to say, first of all, this matrix R we just derived is a square matrix. Right? In our case, it is a 2 by 2 matrix over real numbers, but it is a 2 by 2 matrix, so it is square. Second of all, and this is really, really special, the determinant of R is 1. Right, so let's go for this again. We had cosine phi minus sine phi, sine phi, cosine phi. The determinant of the 2 by 2 matrix is easy to compute. It is just this element times this element minus this times this, but this is the determinant of this is cosine square of phi minus something minus is plus sine square phi, and this is 1. So this is a matrix whose determinant is 1, very special. Third of all, and it becomes more special all the time. Look at this. The column vectors, first column vector, let's call this one, I don't know, column vector 1, and this one is column vector 2. These two numbers form a vector, two-dimensional vector. These two numbers form a vector. They are perpendicular, orthogonal. Yeah. It's an orthogonal matrix. And to say that it is an orthogonal matrix is indeed to say that the two columns are orthogonal, but not only the columns, also the rows. This is really very, very special here. It's indeed an orthogonal matrix. R is orthogonal. And I just said what that means. That is to say that the columns are orthogonal and the rows are orthogonal. And because of this, and this is now where it really gets crazy, the inverse of R, so that is the matrix R inverted, or R inverse, is actually the transpose. Now, what I have written down here holds for this matrix. How do I stress? This is not a general property of matrices. Right? Like, so this equation here is something extremely special, and it applies to this matrix. But this does not at all hold in general, but here it does. And so because of all these crazily, being square is not that special. Having a determinant of 1 is special. Being orthogonal is even more special, and if these things are given, then it's very special indeed. Because of these four properties, this is what we call a rotation matrix. Or any matrix that has these things is a rotation matrix. Does not have to be a 2 by 2, can be a 1000 by 1000 matrix. But if it has these properties, it's a 1000 by 1000 rotation matrix. Okay? Yeah, and I am at a forking point here because either I switch the projector back on, or I talk about groups. You know what? I like the whiteboard, so let's continue with the whiteboard. This is something that we will. What I'm going to tell you now is something we will not really need in the next couple of lectures, but it is probably interesting that I tell you about it, because otherwise you might at points not understand what I say. And what I wanted to tell you is that I can summarize all these things by saying that the matrix R is an element of the special orthogonal group of dimensions 2 by 2 over the real numbers. Has anybody seen this before? No. Okay. Then let's briefly talk about this. So,
Sorry.
yeah.
Can you repeat what you're saying there? R belongs to what? The integral of O2?
Okay. So this. Yeah. I will discuss this now. Instead of me having to say all these four things all the time, I could summarize this by saying that the matrix R is an element of something which we call the special orthogonal group of 2 by 2 matrices defined over the real numbers. And I will now sort of explain what this means. But I will quite frequently, this is because to me it's easier to say something like this than this, and it may happen from time to time that I say that, and then you may wonder, well, what? And so I'll ever so briefly walk you through the notion of a group. And again, this is something we can use later on, not right away, but in the next semester, when we're talking about more advanced image processing. Then this comes in handy, but since we have been talking about vector spaces last time, we'll now ever so briefly talk about another mathematical structure, namely the notion of a group. Groups. And a group is defined, a group is a tuple, I will write it like this, G, and an operation, let's call it times. Remember last time we talked about vector spaces, I said it's a triple of a set V, and an operation, let's call it plus, and another operation, let's call it times. Now we are talking about a tuple where we have a set, let's call it G, and some operation, let's call it times. This is again an abstract point of view on many things we may actually talk about, in particular, say, matrices. And in order for this thing to be what we call a group, it has to meet a couple of actions, just as the vector spaces we talked about last time have to meet a couple of actions. So it has to fulfill the property of closure, which is to say, for every element A and B in this set G, we want that the element A times B is also in G. This is very similar to what happens with vectors and plus. A vector plus another vector is another vector. Here we have an element of the group times another element of the group is another element of the group. Should be associative. Associativity, which is to say that if we are talking about three elements, let's say A, B, and C, in G, we want that it doesn't matter if we first say multiply A and B and then multiply C, or if we first multiply B and C and then multiply A. That should be the same thing. Then there is supposed to be an identity, which is to say that there exists an element, let's call it E, I know, E, in G, with the property that if we multiply to another A, it's the same as if we multiply A and E, gives us A. So this is similar to this notion of the zero vector in a vector space. If we add 0 to something, nothing happens. Here we have an identity element. If we multiply to something, nothing happens. And then finally there is an inverse. An inverse that is for each A in this group, there is supposed to exist a element B in this group, such that if we multiply A and B, is supposed to be the same as B times A, should give the identity element. Now, think of what you know about matrices, right? We, for instance, what we just saw was a 2 by 2 matrix. If we multiply two 2 by 2 matrices using what we know as matrix multiplication, we get another 2 by 2 matrix. So this seems to hold for 2 by 2 matrices, right? Of course, that does hold for 3 by 3, 4 by 4, whatever, right? We also know that if we are talking about 3 matrices and we multiply them together, it doesn't make a difference of whether we first multiply the first and the second one and then the third one, or first multiply the second and third and then the first one. Like matrix multiplication is associative. There is an identity matrix. This is this matrix with all ones along the diagonal and zeros otherwise. If we multiply that matrix to any other matrix, nothing happens. Not every matrix has an inverse. Not every matrix has an inverse, right? But certain matrices have. And so therefore, if we are talking about matrices that have an inverse, and that is basically to say, let's talk about the set of matrices for which the determinant is not 0, and make them square. So M is some n by n square matrix. Right? This set forms a group. We are talking about matrices that are square. If we multiply two square matrices, we get another square matrix. And if we also require that this set only contains matrices that have an inverse, which is to say they have a determinant that is different from 0. But this is a subset of all the matrices there is, but we focus on this subset. And this set of matrices fulfills all these things. So we know that this set, together with the operation of matrix multiplication, forms a group. And this set forms a group that is called this set, together with the operation matrix multiplication, so this is the tuple here, is known as the general linear group of the n by n matrices defined over the reals. Right? We have n by n matrices defined over the reals, and we want them to be invertible. And if we consider this set together with this operation of matrix multiplication, it is a group. This group has a name, general linear group, n by n matrices over the reals. Right? We can furthermore require that the determinant is not just different from 0, but actually 1. I'll do this again. I'll erase all this. So if we are talking about this construct here, a set of matrices which are elements of the n by n matrices over the real numbers, and their determinant is different from 0, and we consider the operation of matrix multiplication. This is a group according to what we just learned about groups. This group is very important. It has a name. Everything that is important has a name, and this name is once again general linear group n over the reals. Now, if we would consider the following thing, a set of matrices where these matrices again are square matrices over the real numbers, and this time we would want that their determinant is actually 1. And then together with this operation of matrix multiplication. This is another group. Can be proven that, like, if you have a matrix that has these properties and you multiply to another matrix with these properties, then you get another matrix with that determinant 1. Has also a name. This is called the is it SO? Wait. Orthogonal group, I guess. I have to be careful here now, I don't really. Orthogonal group over the, no. the special linear group over the n by n matrices. This is obviously a subset of this. And the one we just talked about, the rotation matrices, they are the set of matrices, again, in general, can be of extension n by n over the real numbers, and their determinant is 1, and they are also orthogonal. It's another property. See, it gets more special ever the further we get here. Again, with operation times. This is the special orthogonal group n r. And we met one instance of these things with respect where n was, with respect to where n was 2. Okay, and I have just done that because it may happen that in our future discussions I use these things. And I may use a thing that we have not discussed right now, but at least from now on you should know, he's talking about groups again. Okay, so most frequently I will refer to this one. And I'm doing that because instead of saying it is square, it has determinant 1, it is orthogonal, and the transpose is the inverse, instead of enumerating all this all the times, I can just say it's an element of this group. That's all. All right? And yeah, now that's that. The take-home message is that rotation matrices are very, very special, and they form their own group. And we have seen now where they actually come from. Right? So when you read a book on computer graphics, or I don't know what kind of books where they talk about rotation matrices, it is, in the end, we walk through it, just an exercise of manipulating equations, and they pop out. Okay? So here is the result we just obtained, and here are the properties we just discussed. And let's ever so briefly continue our discussion for the most important thing has been said. We now understand what a rotation matrix is. Right? And if you understand that, then you basically, I cannot emphasize that enough. If you really understand the concept of rotation, you understand half of what I can teach you. Okay. What we are after are transformations of coordinates. And we said that we're talking about coordinate vectors u and x, and we just saw how we can, if we're given a vector u, how we can turn it into a vector x if they are rotated, like the corresponding coordinate systems are rotated. Now, in this lecture, what we are really interested in is the effect the transformation of coordinates has on a function. Right? What we are interested in is images. Let's call it G. An image G, say this picture of asterix and obelix, which is a partial function defined over a domain which happens to be a set of two-dimensional coordinates. And what happens if we manipulate these coordinates? What happens with G? And to express that, if we manipulate these coordinates using matrices, later on we'll use general operators, but if we are given a function G of u, and we do something with the u, like as we just did, that will somehow produce a new function, and we call that G tilde. And instead of writing matrix M times U, I'll write X. And this thing here means this. So, here is a function, g of u. It looks like an image, and indeed it is an image. And I have singled out a point with coordinates u and v. Can you see the red crosshair here? Okay. It's actually this upper right corner of the image. I actually have this black border here. So, this function is called g of u, and I have singled out a particular point. And now I have produced a new function, and I call this one g tilde of x. So this is obvious if we look at it. This here is a different function than this here. Okay? This one is called g of u. This one is called g tilde of x. But note that, again, I have singled out a point here, x and y, that for this function here, at this point, it has the same value, a white pixel, as this function at this point. This is what I want to express with this equation. When I say, and this is a convention we will use from now on, that we are given a function g of u, and we produce another function g tilde of x, and they are supposed to be, like there is an equal sign here. You have to read it as, okay, this is the function we are given. We create a new one. But at certain coordinates, this function has the same value as the original one. Okay, this is how we read this equation. And what we do here is we create this new function by doing something with the coordinates of the original function. That's all. We change the coordinates, not the value. Like this is still a white pixel. It is not. It has not become a blue pixel also. We have just sort of changed the coordinates, not the value of the function. Okay. We spent quite some time talking about matrix realizations of the affine transformation of rotation, and other affine transformations in the plane can also be realized in terms of matrix operations. For instance, if we want to scale by a factor of a along the x direction or b along the y direction, we could use these matrices here. Those are scaling matrices. If we want to scale along x and y simultaneously, voila. If we are interested in shearing, this is the way to go. Right? We have this ones along the diagonal, and then number c, an element c, here at the upper right-hand side corner of this matrix. That would create a shearing along the x direction. This one would create a shearing along the y direction. We want to shear about like both directions, that we can use that afterwards. What else do we have? Yeah, these transformations that would flip the coordinate system or mirror it about an axis or a point. This is mirroring about the x-axis, mirroring about the y-axis, mirroring about the origin. Can also be done using matrices. What about translations? So we said affine transformations include identity, doing nothing, rotation, shearing, scaling, and transformation. Okay, if we want to, yeah, well, whatever. We just discussed that if we want to apply several transformations, we can apply them in a row is also another affine transformation. And of course, if we multiply several matrices to something in a row, we can first multiply the matrices, get a new matrix model. So we can compose them as to our likings. But what is about translation? Here's another example. This is, okay, so sorry, I'm ahead of myself. Take a step back. We can combine several affine transformations, which we may want to realize in terms of matrix operations, into a new, more general one, right? But when we do that, we have to live with the fact that matrices may form a group, but the group is not commutative. That is, if you multiply 2 and 3, you get 6. If you multiply 3 and 2, you get 6. It's the same thing, it's commutative. But if you multiply matrix A to matrix B, it may not be the same as if you multiply matrix B to matrix A. Okay? Matrix multiplication is not commutative, and we can see this here. Here's the original image. I have produced a new image where I rotated the coordinates, and after I did this, I produced yet another image where this is a rotation, this is a shearing, and here I first rotated and then sheared, and here I first sheared and then rotated, and you can see looks different. Right? And this is because the product S times R is something else than R times S. If that was commutative, that is to say, it doesn't matter in which order we do it, these two images would look the same, but they do not look the same, and this is because of this important caveat. Matrix multiplication is not in general commutative. Okay, and now finally translations. Rotation, shear, scale, reflections, that can be done using matrices. Right? Whenever we can express something in terms of a matrix vector operation, we know that we're talking about a linear transformation. A linear transformation is defined like this. We can specialize that for our context. If we are, say, talking about the vectors, u and v, and we have a transformation, such as the rotation, which we can realize in terms of a matrix multiplication. I will now say the rotation is called T for transformation. We have a transformation, and if it doesn't matter if we apply this transformation to u and then add the result of the transformation of v, if it doesn't make a difference whether we do this or we transform u plus v, that doesn't make a difference, and at the same time this doesn't make a difference. If we apply the transformation to u and then multiply something to it, or if we apply the transformation to u multiplied by something, alpha in this case. If t obeys this, then t is called a linear operator. And matrix multiplication does obey this. And finally, I should switch the order of these slides. I said that affine transformations also include translations, moving something from here to say here. And a translation can be expressed like this. But this is not a matrix multiplication. And it's not linear. So, because of this, I said affine transformations include rotations, shear, all these things, plus translations. Because of this, we can now accept that in general, the most general affine transformation we can think of for points in the plane, let's say, to keep it easy, can be expressed like this. We have a vector on the left-hand side of the equation sign. Then we have the vector we are starting with, which is being transformed by a matrix, and something is added to it. This is the most general form of two-dimensional affine transformation. And again, because I do not want to write these 10 symbols all the time, I just may express it as I already did this. This becomes vector x, this becomes vector u, this matrix is M, the translation vector is T. Okay. And what I really want to stress is that affine transformations consist of a linear part and a translation in general. And because of that, they are not linear operations. And to see this, and I really have to stress it because this is the most frequent wrongly answered question in the exam. So this semester I stress it. When I say that an affine transformation is not necessarily linear, I can convince you by looking at this. Let us stick with what we just saw. An affine transformation of a vector u is m times u plus t. Now then what happens if we apply this to u plus v? Right? Well, we plug this in here, so m times u plus v plus t. And this here is m times u plus m times v plus t. But this is not the same as m times u plus t plus m times v plus t. There's two t's here where there's just one t here. But this would be the result if we had t applied to u and t applied to v. Right? So once again, here for this general form of an affine transformation, this here is not the same as that. Believe me, if I ask this in the exam, you tell me, no, it's not a linear transformation, right? And actually, the crazy thing is, this is also the thing I have to discuss most often in detail once we discuss the results of the exams. But I have it here, yeah, but it's not linear, but yes. I said, no. So once again, for something to be linear, it has to obey this, okay? And we blissfully ignored this one here. We just sort of looked at this property. And I just walked you through the fact that for this transformation, it is not linear. Okay? Believe me. And we can summarize this by saying that every linear transformation is affine, but not every affine transformation is linear. Okay? And this is actually, when I say this is the most wrongly answered question in the exam, this is something I often ask in the exam, right? Just to see if you have learned something. And well, every linear transformation is affine, but not every affine transformation is linear. Okay. All right. Then we can summarize what we have learned today, or at least discussed today. We have discussed, based on what we did last time when we started talking about coordinates, we have now looked at the first simple cases of coordinate transformations. And in particular, we focused on this idea of affine transformations. And once again, for the case of two-dimensional coordinate vectors, the general affine transformation is given by some matrix applied to the vector plus some transformation. This is what we understand as an affine transformation. And we looked into different types of affine transformations and and this is by far really the most important thing we did today, tried to understand the ideas behind rotation. And we went through it like in a really elementary manner because it would be great if you understand that these rotation matrices basically result from doing inner products with equations, which allows us to rearrange these equations, which allows us to solve these equations for unknowns. It's a very, very, very close connection between these inner products and these rotations, and you have seen how these rotation matrices come about. We then spent, that was sort of an excursus, ever so briefly talked about the fact that in addition to these structures such as vector spaces, mathematics knows so many more structures. We talked about groups, and we saw that these rotation matrices form a group, which is very, very special. It's so special that it has the name special orthogonal group. So we talked about rotations. And again, a very important take-home message, and this is really important. Not to confuse affine transformations and linear transformations. Once again, every linear transformation is affine, but not vice versa in general. So that is sort of the briefest summary I can give of what we talked about. And for those of you who want to put your newfound knowledge to work, look, we just introduced the idea of a linear transformation, and then we said that these kind of affine transformations are not linear, and I proved it with respect to this property. Can you probably achieve the same result with respect to this property? Think about it. And for those of you, I mean, I don't know, who's taking courses in computer graphics? Okay, you might be able to answer this question. Is there a way? You already know. Okay. Okay, so you may already know it, but you may sort of think about it again, because we'll do that next time as well. So is there a way of turning these things, these affine transformations that are not necessarily linear, into something linear? Can we do that? And how? We'll talk about it next time. That is all I have got for today. Are there any questions? Yeah.
When we talk about the rotation, actually we rotate the axis, is not the object.
Yeah.
So if we...
Okay. Yeah. Her question is about if we rotate the axis or the object.
Yeah, so if we rotate the axis, it
Yeah.
means if I do other transformation like scaling
Yeah.
or translation, all I need to deal with the axis, not object.
Yeah.
Or, okay, so...
Yeah, okay. Yes, indeed, right? And say if you did some say shearing, then what you do is go from a coordinate system like this to a coordinate system like that. Here, if you shear this, you end up with X level. The reason why I said that if we do these transformations, we can think of them either as doing something with the object or doing something with the coordinate system. And the reason why I said let's try to think of it as doing something with the coordinate system is because if we think of it like that, we can say that the point is the same. Like this point does not care about whether we want to talk about it with respect to the xy axis or the uv axis. So I said if we understand these transformations as doing something to the coordinate systems, then we can have this equation we had where we said x times px plus y plus times py equals u times pu plus v times pv. That is easier to accept if we say let us transform the coordinates. Right? If I said let's do something with the point, then this equation would not make so much sense. But don't worry, it is the same. We can think of it as doing something to the object or doing something to our point of view. Okay? I, as a student, preferred to think of it as doing something to the object because it looks as if we do something to the object. As a professor, I prefer to think of it as doing something to the coordinate axis. And that takes a couple of years, but yes, it's true. So don't worry, you can think of it either way, I don't care. I now prefer thinking of it in terms of doing something to our point of view than doing something to the object. Okay? Any other question? Great, so then we see again on each other again on Monday, right? Yeah. Bye.